mit Schnellspannvorrichtung. Oh, bitte funktioniert. Also so hält man es dann. Ja! Ja! Ah, ich werde nicht mehr. Ja! Moin Moin YouTube! In a previous video I showed you guys the design journey of this thing right here, my almost 100% 3D printed pistol crossbow, well, glow-in-the-dark pistol crossbow. Now, like I said in the past video, I'm quite satisfied with it, but I'm not satisfied with it. You know, there's a long list of issues with it. It's super wobbly, it comes apart super easily, the bow clip here, you can possibly see it, the bolt clip is just super weak, and the bow itself is just not very strong. So I wanted to iterate on that and create an actually working product that is, you know, working. So the list of requirements for this was long. You know, it was supposed to be easy to print, little to no supports, to not produce much waste. I wanted to have a swappable bow in the front to increase or decrease the power. I wanted it to be durable. I wanted to have a bolt clip that probably works, a loading mechanism, it should be precise. And on top of all of that, again, as 3D printed as possible. Now, don't ask me why I did that, because it was a nightmare to get there. It worked out in the end, but wow, that was quite the journey. Now, talking about all of that would be much too long for just one video, and I'm already prone to talking quite a bit. So I've boiled it down to 4 things that I would like to show in this video. Part 1 is how to design a working PLA bow for that thing. How to design a reload mechanism. Number 3, how to design a properly functioning reload mechanism. When we get to it, you'll see what I mean with that. Number 4, which string to use for such project to, you know, get it to work. This video now will have 2 parts. Part 1 will be me, you know, going over the design and engineering challenges, and part 2 will just be me shooting stuff. So in case you don't care about the engineering bit, just skip ahead and enjoy. Let's talk about the bow, like this one right here. When you're trying to 3D print a bow, there is mostly 3 things you need to take into consideration. Number 1 is the printing direction, number 2 is the distribution of force, and number 3 is the bow power itself. Now, talking about printing direction is pretty straightforward. As you might know, whenever you work with an FDM printer, the object that you're printing gets constructed layer on layer on layer on layer. Now, if you try to print a bow vertically, which is, you know, this direction right here, there is an issue with that, because when you use it as a bow, which has this direction, you essentially have layer on layer on layer on layer, all the layers here as sort of built-in breaking points, which I can show you quite easily. See? One more time. Doesn't really work. Now, the fix for that is pretty straightforward. What you really just need to do is change the printing direction so that you're printing that thing horizontally, and that really gives it, as you can see, quite a bit of flex and makes it much more usable as a bow, because now it's printed, you know, again, layer on layer on layer, but in a direction that doesn't put in breaking points into the bow. Now, that alone doesn't protect the printed part from snapping, or doesn't protect the bow from snapping though. As you can see on this example right here, which is also printed in a horizontal direction, but still, it snaps. Now, let's take a look why that happens, and because this is about the distribution of force. To get an understanding of distribution of force, let's take a look at a quick example. Here we have a rather small bow, and we have 3 points of interest that we need to talk about. On each end of the bow, we have the anchor points for the bowstring, and there you have about 50% each of the total draw weight. So say we have a 30-pound bow, then we have 15 pounds of force on both ends. Now, that isn't too bad, but the part that we need to worry about is the center of the bow up here.
because here we have an equal amount of force as we have in the bowstring, which, you know, we kind of have to have there. And we need to make sure that this part of the bow can take that force. Because if we don't, what happens is, you know, the force increases until it snaps. What we need to do to fix this is really just increase the surface amount or the volume at that point, so that all of the force can be distributed into a bigger area.
Last but not least, bow power. Now, to increase the power of the bow is pretty straightforward. You just need to make it thicker. This one right here, it's about 45-pound bow, is about 1 centimeter thick and about 4 centimeters high. 4 centimeters high because, you know, distribution of force, considering that this is 45 pounds of weight when it's charged, you need to have quite a bit of surface area for the force to be distributed in to prevent it from snapping. Now, I didn't do any kind of linear regression to get to the science of the dimensions of this thing. What I did was pretty much just a pretty long and intensive trial run by creating different kinds of bows and just marking down on the bow itself for how many shots it lasted. This bow right here, for example, though, and this is the result that I'm currently working with, like I said, 45 pounds, 1 centimeter thick and about 4 centimeters high. This one lasted for 200 or 300 shots so far, and it doesn't show any kind of sign of deterioration. So I'm quite satisfied with that result. So we have a bow. Yay! Problem is, the bow itself doesn't really, you know, help much. Of course, you can charge this thing by hand. You know, let me demonstrate real quick. You basically grab it like this, put your thumb here in the back. This bow here, I think it's old. I think it has like 50 pounds of draw weight. And to load it, you have to hold it like this and then pull this back by hand. Whoa, super uncomfortable. And, you know, not comfortable with having it this close to me while I'm reloading it, actually. And the biggest issue with that is there's two. Number one, those are 50 pounds that are here in this bowstring. So grabbing it like this, you always have this string cut into your hands, which is just very uncomfortable. And number two is there is a chance of loading it unevenly by pulling on one side a bit stronger than what you're pulling on the other. So a reloading mechanism is very, very, very helpful for that. Now, designing that, remember the clip that I showed in the intro where I was kind of overcome with joy? Yeah! Yeah, getting there took quite a bit of fiddling, and on top of that, a couple of injuries.
First things first, we need a basic crossbow. For that, we need a body, a trigger, a bow, and a bowstring. Now, to shoot this, you basically pull the bowstring all the way back into the notch, and by pulling on the trigger, you release the bowstring and pew.
Which is how this thing here works, but like I said, super uncomfortable.
One way to address this is by adding a jig. So we add a little slat that catches the bowstring, give it a handle in the back, and by pulling on the handle, we basically get the bowstring into the notch, and then it's the same procedure.
Remember the pictures of the injuries I showed you earlier? Yeah, both of them come from that solution because I totally underestimated the forces and something would always rip, you know. The one where I basically sliced my arm open right here, I was pulling on the back to reload it, it ripped, and then I kind of sliced my arm open. And the other time, well, that's the more embarrassing one, I pulled on it, it ripped, and I basically hit myself in the head with a handle. Yeah, not my proudest moments, I admit. Now it was great that I got it to work, but there was no mechanical advantage by using that reload mechanism. You know, you would load the pistol crossbow evenly, but say it was a 50-pound bow, you'd actually have to invest 50 pounds of power in the back to cock it. Now, looking at a couple of examples of pistol crossbows that are sold commercially, I found a couple of solutions that utilize lever in the back to reload it. So I decided to give that solution a try.
Now for that solution we still need a slat, but now we're going to add a lever in the back and a little grip in the front for usability. Now we reload this by pushing down the lever, which will pull the slat back and then get the bowstring into the notch, and you know, the firing mechanism still is the same, but the slat will catch the bowstring, and then basically by just repeatedly using the lever you reload the crossbow.
Now, a couple of you guys will already have seen what the issue with this design is. Basically, the problem is that, which makes sense, a lever is relative to the forces applied to it. I mean, if you know the bow was to pull the slat down, then this would work, but it's pulling it horizontally. So the design that I have here makes everything mechanically much worse instead of making it much better. Let's take a look at that.
Let's take a closer look at the iteration that you just saw in the clip. From this basic setup, we have sort of seesaw, and by applying forces here in the back and by pushing this lever down, you would usually get the front to rise. But because we have additional pivot back up here, I figured, okay, what would happen is instead of moving the other side, the front side up, the sled up, we would pull it back, and basically by doing so, load the crossbow. Unfortunately, that's not how it works. Like I said, the forces are relative. So let's do a little bit of visual magic here and load this thing halfway and add a couple of visual helping lines to show what's happening. And as you can quite clearly see in this visualization, the effort arm is very short compared to the resistance arm, which is the upper one. So we actually have a disadvantage of about 5-to-1. And that's just a terrible design. Now by cocking it further or levering it further, we actually get back to a 1-to-1, let's call it nothingness or equilibrium, but still there is no advantage by using this lever.
Yeah, we need to make that thing smart in its design. Well, I'm a software engineer, I'm learning this by experience, not by trade. Luckily, making that thing working a bit better wasn't all that complicated.
Essentially, all that I needed to do was lower the point of effort on the lever at the back. So now when we cock it halfway, we, well, at its peak, have a 1-to-1 equilibrium, nothingness, however you want to call it again. But as we get closer to the end of the levering, we actually have a 2-to-1 advantage, which significantly lightens the amount of force that you have to invest into it to load that crossbow.
And that makes all the difference in the world. I mean, this is a 45-pound bow, and as you can see, super easy to reload. Let's talk about the bowstring. Now this won't be a quick one, I promise. First of all, whenever you 3D print something, you will never have a 100% smooth texture to it. You can see it here. This is my R&D bow, basically. You have a rather rough sandpaper-like structure. Now, first, you really want to rub some wax in there to even it out a little bit, but that only gets you so far. Now, I used to use exclusively paracord when designing this or when building this. This is this right here. The problem is paracord is still made of a lot of little fibers that, by rubbing over the surface plenty of times, they gets chewed through quite quickly. So it works, you will be able to use it for like 50, 60 shots, something like that. But if you want to get anywhere for a longer time, then I'd really recommend using Dyneema. Dyneema is a material that is awesome. It has a very different texture than the paracord does. Even cutting it is a lot harder. You know, while with paracord you just take scissors and cut them off, with Dyneema you really need to use basically a knife or something and cut through it. And that stuff lasts a lot longer. I think the one in my bow that I'm mostly using for playing around with has lasted for like 150, 200 shots so far, and well, they'll show a little bit of deterioration. That happens to every bowstring, you know, it's friction, but it lasts very long. And that is really it. Well, almost really it. Unlike what I've teasered in my previous video, I haven't shown the version with a magazine just yet. It's just not ready. It still needs a bit of fiddling. It works, but it's still prone to jamming and stuff like that, and that wouldn't make much sense. Anyway, I hope you enjoyed it. I personally am very happy with the result. I mean, you know, it's a robust, actual product level thing by now. It is like I wanted it to be, basically just 3D printed except for the bowstring. It's durable, it's working, it's functional, it's actually fun to use, it's accurate. So I'm really, really happy with how it turned out. And, you know, it's a satisfying feeling of having created something that is actually developed properly. Now, will I be releasing the plans so everybody can print one of those at home? The answer to that is no. I mean, I've had those plans for a long time, and you know, had a lot of time to think about it, and I just don't feel comfortable with putting up plans on the web so that people can produce weapons en masse at home that are potentially very harmful. I mean, remember, there is no metal in it, so it's not even detectable by a metal detector, and whichever of those is produced at home will be basically untraceable. And on top of that, I know that the bow can be pushed a lot further. I mean, I've tried it, and you know, going of 60, 65 pounds is easily possible. It's not durable then, but it's possible. And I just don't like that idea. Sorry. I'm filthy, liberal, socialist, German scum through and through, totally. And I just take a bit different there. Now, for the engineering guys out there, I believe this video has given you tools to design this yourself. What do you do? That is up to you, is your thing. Now, not saying that I won't do anything with it. You know, I quit my job about half a year ago, and I'm getting to the point where I actually have to earn some money again. Like I said in the video earlier, I used to do management, but get a little bit fed up with it. And so I'm thinking about creating a soft LARP compactable version for this that I will be selling over on Etsy. You know, something there people can just do a little bit of target practice with at home and play around with a little bit without it being able to do actually much harm. Yeah, but still thinking about that, still haven't done that, so we'll see about that. Thank you very much for watching. If you like this video, check out one of my other ones that might be well, somewhere. And leave a comment down below, subscribe to the channel, and well, by now you know how all this goes. Until next time.